Okay, all right. Welcome back, everyone. This is the last lecture. Yes, I know. Parting is such sweet sorrow, but it happens. Okay, so to remind you where we were last time, I introduced a theory called BF theory. Is this? Yeah. Called BF theory, whose action was the following. It involved a one-form and a two-form gauge field. And the action was equal to In over 2 pi. It's defined on an arbitrary 4 manifold. And the action is just B wedge dA. Okay? And this is B2 wedge dA1. I'm going to start omitting the subscript soon. This is just to remind you what the formuleness of each of these things was. And this is a topological quantum field theory, which means that it does not care about geometry. Okay? In particular, it is coordinate independent without a metric. There's no metric in here. So you can basically use coordinate transformations to move these things around however you like. And that means that you don't expect any local degrees of freedom. There are, however, global degrees of freedom, which we're going to talk about now. So, and also let me just remind you that there are the following gauge redundancies. These are gauge fields. So the theory is invariant under the following gauge transformations. Here lambda is a 1 form, and A1 goes to A1 plus d lambda 0. Little lambda is a 0 form. This is a gauge redundancy under which everything should be invariant. And then the very last thing we did last time was we demanded invariance of this under large gauge transformations, where I'm using large gauge transformations in the way to mean gauge transformations who are not connected to the identity but are still gauge, which I stress is the exact opposite way as it's sometimes used in the literature. So just be careful. But that's what I mean by large gauge transformations. And if you think about that, then what that implies is that the parameter n has to be in Z. Okay? It's an integer. You can take it to be a positive integer with no loss of generality because the choice of orientation on this flips the sign of this. And this makes sense because this whole thing was meant to describe, I forgot about the motivation, this whole thing describes a spontaneously broken one-form symmetry in 4D. Okay? So in fact, it is a good thing that n is an integer because it's describing something where n has to be an integer. So this is a feature, not a bug. Okay. Any questions about this before we keep going? Is everyone happy with this? Yeah.
In what sense do you mean they're not continuously connected to the identity? Because like if we're working with continue with the connected.
Oh, yeah, absolutely. So if you recall, the gauge transformation that I used to do this was the following. I thought about the theory on S1 times S3. And then the gauge transformation was lambda naught equals to phi, where phi moves around the circle, okay? So this thing is not single valued. When you come back to itself, lambda naught does not come back to itself, but e to the I lambda naught does come back to itself, okay? This thing winds around once around the circle. That's what I mean by continuously connected, not continuously connected. You could not put a parameter alpha here, because if you, oh yeah, that's right, yeah. This will be only a tiny bit though, so I'll go back in a second. So this lambda naught, each of the I lambda naught winds around once. If you put a parameter alpha here, alpha must be an integer. Otherwise, it's at non-integer levels of winding. Okay? That's what I mean by not continuously connected. Alpha is 0 or 1 or 2. It cannot be 0.00001. Okay? Does that make sense? Yeah. Note that this is not, there is no problem. The fields here are still smooth, but still there exist discrete structures. Okay? Excellent question. Anything else? I'm going to erase this because I'm not really sure the factors are right. Okay. Now, good. So, now n is quantized, and this is again what you expect to happen. Just as a general statement. Oh, yeah, that's right. This is a general statement. Topological quantum field theories are discrete rigid objects. Did it work? Yeah, okay. Are discrete rigid objects, and so it makes sense that they should have no continuous parameters in their description. All right. So now, let's remind ourselves, what is the goal in this? We're trying to describe a spontaneous breaking of a one-form symmetry, and it's a discrete one. And we need to be able to describe the topological objects in the theory. In other words, the charged line operators and the Gukov-Witten surface operator, which generates the charge. So we need to be able to describe W of C1 defined on some closed 1 manifold and G of M2, the Gukov-Witten operator defined on some closed 2 manifold. So I have to tell you, I have to realize these guys in terms of these fundamental fields, B and A. Okay? And there's really only one way to do this. All right? W of C1 is defined in terms of these low energy fields as the exponential of I. Oh, I messed this up. Exponentiating does not commute with integration. It's the exponential of I A1. Put the I outside. C1. And G of M2 is similarly the exponential on M2 of B2. Okay? This should seem very natural. Okay? Let me just point out a few things about these definitions. W used to be labeled by a sort of a W was previously in the fundamental of the gauge group, but really you saw it's just generating a phase, right? So I'm just going to take both W and G, who was labeled by an element of the center previously. I'm looking only at the minimal ingredient in each class, the charge 1 element, okay? If you square it, you get the charge 2 element. If you take n copies of it, you eventually get something trivial. But this is just the minimal element, and this is just for convenience. You can easily put a factor in here, there, and there to get higher charge elements, okay? There's no problem with that. And these two things are invariant under these gauge transformations, right? So this is invariant under gauge, by which I mean these guys, as they have to be, okay? Because if you do this gauge integration by parts, you just get a boundary term which is 0, provided these objects are closed. So they have to be closed, and again, that's what you want. Okay. Now, all right. So now I'm going to tell you what the point of this is. If you recall, the point of these objects is that W and G are meant to have a non-trivial linking, right, in space-time, because that's the point of the one-form symmetry. And now it turns out that if you now try to evaluate a configuration of these guys, so if you use this theory to evaluate, for example, the following correlation function, W of C1, G of M2. So in this theory, you can evaluate, say, the two-point function of this thing. Then what you find is that this thing goes like the exponential of 2 pi I over n times the linking number of C1 and M2. This is the linking number of these two manifolds, okay? And again, linking number is a well-defined concept for a 1 manifold and a 2 manifold in 4 dimensions. This makes sense, okay? So here's an example of two things that link. Here, let's say this is C1 and this is M2, all right? These two things, a 2 surface and a 1 surface, can link in 4-dimensional space-time. This is actually, of course, again, for the same reason, this is a picture of two 1 manifolds in 3-dimensional space-time, and it's the same geometry, it's the same idea, okay? Maybe it's a good time to say, in general, a P manifold and a Q manifold link in D-dimensional space-time if P plus Q plus 1 equals to D, okay? That's the general relation, and you can think about that and look at your shoelaces and think about why that's true, but that's the general formula, okay? Okay. Now, this is what we want, okay? So this is, I stress, this is the desired relation, because this means that we have the one-form symmetry. Okay? Right? This is the statement of the one-form symmetry. The one-form symmetry is exactly when we have the linking relation. And furthermore, it is spontaneously broken because in this theory, W1 of C has a It does not, the right thing to say here is, it basically doesn't depend on anything, okay? It does not have an area law. It actually doesn't depend on C at all. Okay, so it has an extreme version of the perimeter law where the coefficient in the perimeter is actually 0. Right? Okay. Now, so does that make sense to everyone? Why? So does it make sense to everyone why this is what we want? This is the desired relation. Okay, this is exactly the linking relation that I've shown you before many times. Now, what I should do now is, I have not proven this to you. I'm just telling you this is what happens. Okay? This is what happens if you calculate this in this theory. Now, the calculation to do this properly takes a little while. So I'm just going to sketch why this is true. Okay? I'm not going to do it properly. So I'm just going to sketch it, and there are more details in the notes. And there also, this is worked out in some detail. This goes back to the fundamental work on Chern-Simons theory by Witten, where it set off this whole thing and eventually got him the Fields Medal. What he just showed is that in Chern-Simons theories that are like this one, the answers to what Wilson lines do when you link them is given by topological invariance of the Wilson lines. This is an example of a simple topological invariant. Okay? So it goes back to that, but I'm just going to sort of schematically tell you why this is true. Okay? So to understand this relation, what you should do is imagine looking at the on-shell action, okay, with these two things inserted. So say I want to calculate this. What you would do is you would look at this thing. So you imagine doing the path integral, okay, over dB and dA in the presence of those Wilson lines. So what am I path integrating over? I have first that action over there, so in over 2 pi, all right, times this thing, okay? And now I'm calculating this object. So I should also add plus I. So this is over the full 4 manifold. I should also add plus I A1 and then plus I M2B. Okay? And this is that expectation value, W of C1, G of B2. Okay, that's this thing here. Does that make sense to everybody? All I've done is I've put in the definition of these two operators and used the action, which says you should weight this by that. Okay. And now, to see this phase, you can do it semi-classically by just varying this action. Yeah.
I guess it's not important.
Yeah.
A minus sign.
Probably.
Minus.
Where's the minus sign? Oh, because you're saying each of the IS is each of the minus IS?
Or
Yeah.
yeah.
Each of the minus S. There probably should be. I don't want to put it in because I worked it out with the other sign. It doesn't really matter. In this case, it doesn't matter because this is sort of why the I is there. The sign of this thing is not really unambiguous because you need to pick an orientation of the 4 manifold. So the sign does not matter. That's why the I is there. Whether you get plus I or minus I depends on the that thing. So yeah, I don't want to put the minus sign in there because it will spoil what I'm about to do, which I worked out with the other sign. But yeah, okay. It's really a convention choice is maybe the thing I'm trying to say. Yeah, but good question. Yeah. Okay. So what I now want to do is I just want to solve. I'm going to solve these equations. Okay, in the presence of these sources. So see, I have these things and they look like sources, right, for these fields. I'm going to solve for these equations for B and A, and then plug this back into the action. Okay, and that will give me an answer. All right. So what are the equations of motion? The equations of motion are n. If I vary this with respect to A, then I get that dB equals to minus a delta function with support on C1, okay, of x. Sorry, this is of x. Okay. And similarly, if I vary it with respect to B, what I get is the dA of x equals to minus a delta function with support on M2. Okay. So exactly which signs you get here depend, of course, on what you just said about which orientation you pick for the M4, but at the end of the day, you get some answer that won't care about that. Okay. So note, by the way, that if we didn't have the sources inserted, you just get dA equals 0, dB equals to 0, which means that all the connections are flat, which means there are no local degrees of freedom. There's still no local degrees of freedom, but now these things are non-zero in some way, which is completely determined by this. Okay? Okay. Now, so now what is happening here? We could, this is, by the way, a linear equation. All right? So we could really just solve this equation for A and B. Okay? This is a thing that's done in textbooks. I'm not going to do that. I'm just going to point out that look at what happens here. So first of all, let's now take this and imagine plugging this into here. All right? Then you get that dA is a delta function. Okay? So you're integrating B2 on a delta function, which is the same thing as this integral of B2 on M2, right? So two of these two terms will cancel. These two terms cancel. Okay, that minus sign is crucial for that. And so all that's left is this, right? So what I need to do is I need to find A1, the A1 that solves this equation, okay? And then evaluate it on this integral, okay? So I need to find the A that solves this equation star. So find A that solves star, all right? And integrate on C1. And that will give my overall answer for the on-shell action. All right, everyone with me? Okay, good. So, so we could do that, but I'm going to, again, just sketch how to do this properly. Okay. So let me try to do this carefully. So first of all, I claim this depends on the linking number. So first of all, if they don't link, then the answer is going to be 0. You can see this kind of easily because there's some equations here. If they don't link, everything is topological. You can take them really far away and they will not affect each other. Okay? So let's look at the case where they link once. So I'm zooming in here. So this is C1 and this is M2. And I'm sort of imagining a case where they link only once. All right? And so this M2, I've zoomed in here. M2 could be closing up again later. Let me just not worry about that for now. Okay, just zoom in here. And now this equation here says that dA equals to minus delta M2, which means that dA has support on M2 alone. Okay? Now let me imagine integrating this equation here, okay, over the interior of this. This is B2. This is a two-dimensional ball, which is the interior of this curve, which hits M2 once because it links once. Okay? If I do that, then what do I get? So I'm integrating star over B2. Then I get n over 2 pi times the integral over B2 of dA equals 2. I integrate this over here, which hits this M2 once, which means I get 1 for this delta function. Okay? So this equals to minus 1. All right? I wish I'd chosen the other sign convention because it would be nicer if this was plus 1, but okay, this is life. And now, what is this? Integral of B2, integral over B2 of dA equals 2, the integral over the boundary of B2, which is C1, this thing over here, times A, equals to minus 1. Which implies that integral of CA equals to minus 2 pi over n. And if you recall, that was the only term who survived in this action. Okay? And so what we find is that the on-shell action, S on shell, for A and B, turns out to be minus I 2 pi over n. Okay? And then when you exponentiate it, you get exactly this thing that I have here, this linking number. Okay? So this shows you how this works for linking number 1. And now I leave it to you to convince yourself that if you link more times, you'll get the power of linking and so on. You can figure this out. Okay, does that make sense to everybody? This is how this topological field theory generates topological linking numbers. That's the idea. This is very clunky because the truth is this is a path integral. You have to like gauge fix. There's like a determinant and stuff like this. You have to do many things. You have to prove it's really topological. I've not done any of that. I've just shown you how the classical action gives you the right answer. Okay. Any questions about this, this calculation before we keep going? Yeah?
This is legal because the theory is kosher?
Sorry?
This is legal because the theory is basically free?
I'm not sure it's legal, really. You should really do the determinants and make sure that the determinants don't mess everything up. Yeah. It's probably better that, yeah, I don't think it's that legal. You really should worry about it. The things that you want to worry about are that the UV regulation of this theory does not mess up what I just did, okay? I've not proven that to you, so I don't think that's really legal. There's some ratio of determinants that's important that you want to worry about. This is just a quick statement, yeah. Good. You feel more like it's going to work because it is Gaussian. So that does make you feel like everything will work out in the end, but yeah. Good, other questions? Everyone happy with this? Okay, good. So a theory that has this behavior, okay, is usually called an example of something that has topological order, okay? This is an example of topological order, okay? Topological order is just a name, okay, given to theories that have non-trivial extended objects that have non-trivial linking algebras, all right? And what we've seen is that in this case, topological order is essentially equivalent to having a spontaneously broken higher form symmetry. Okay? They are really basically the same thing. Okay? When you have a spontaneously broken higher form symmetry, then you have objects that have perimeter laws, or even simpler, that have a non-trivial linking, and so they're really the same thing. Okay? In this way, we can realize topological order in the Landau paradigm. Okay? The low energy effective description of a spontaneously broken one-form symmetry is given by something like that action over there, and that's what the slightly older literature calls topological order. Okay. Good. So, any questions about topological order before I move on and do something about ground states? Is everyone happy with this? Okay. So next, I want to do something in the Hamiltonian language. Okay, yeah.
Sorry,
yeah. Please.
This equation of motion.
Yeah.
So this is like meant that there's so we have a free form on the left hand side and no form on the right hand side. There's a, or is it just
No, so this is actually a form. So like a few lectures back, I defined an object which is delta of x as a sub. This thing takes in as a definition a one cycle. It's a delta of x which depends on a one cycle. This is actually a three form. Okay. It is a definition which I gave a while ago. It's really, this is the form, the idea that x, it only has support on C1 and is a form. That's what this delta function is doing. So this is a three form and this is a two form. Yeah. Okay. So it does work out. You can define the forminess correctly. It has some name in math that I don't remember. Yeah. But if you look in the notes, I defined it a while back. Yeah. Good question. Yeah. Some people look more confused than they were before I made this explanation. It's just this is a delta function that just x has non-zero support on C1. That's all that means. And there's some kinematic factors to make sure you can integrate it correctly. Okay. Good. Yeah. This is a good question. These formulas become very lengthy if you try to write them out in coordinates, to be honest. So, okay. Good. All right. So now I want to talk about ground states. Okay. So one of the hallmarks of topological order is that, is that the physics of the system depends on global properties of the manifold that we're thinking about. Okay. So for example, let's not talk about topological, let's talk about normal zero form symmetries. So if you have a zero form Zn spontaneous symmetry breaking, in other words, you really imagine that you have like some potential that it's some periodic potential, okay? Then you have one ground state for each minimum of the potential, okay? It can't do that. Yeah, you get the idea. Okay, now it's identified again here. All right. Then you get n ground states. Right? Okay. If you have a one form Zn spontaneous symmetry breaking, then you can also get more than one ground state, but the number of ground states you get depends on the topology of the spatial manifold. Okay. Something important has just happened. Anyway, topology of space. Now, I'm now going to show you an example of this. Okay. So let's consider quantizing that theory. So let's quantize, BF theory. 1 second. Okay. Let's quantize BF theory on R cross S1 cross S3. Okay. So here this R is time. All right. And so I'm quantizing it. So that means you should imagine this is space. Okay. So I'm quantizing my BF theory on this non-trivial spatial manifold. Okay. I pick this as the simplest spatial. Oh, sorry. Okay. I pick this as the simplest spatial manifold that has some non-trivial topology. Okay. Now, this is actually the first time that in these lectures that we're doing anything in a Hamiltonian picture. Okay. Everything else has been path integral so far. We're now going to do some Hamiltonian stuff. All right. Again, due to lack of time, I'm not going to do it carefully. I'm just going to make some statements. And we can check them in the exercises, okay? But they're all quite easy to check. This theory is it's a quadratic theory, so you should be able to quantize it with no problem at all, okay? So it's really quite simple to do this. So, so I'm just going to note some points, and we should verify these points. We can do them in the tutorial, or you can do them as homework. So, first of all, number one, so this is Hamiltonian quantization. So you should just apply the normal rules that you know from your quantum mechanics class to this. You know, find the canonical momenta, make sure that they have the right commutation relation, blah, blah, blah. You're going to just do that. Now, the first thing is that, first of all, there are no local degrees of freedom in the theory. Okay? If you, this really comes because the equations of motion, dA equals 0, dB equal to 0, really just set all local degrees of freedom to 0. That's why. Okay. However, there can still be some states. Okay, there can be states, but they're not local. All right, they're kind of delocalized over the full spatial manifold. Okay, they're delocalized in space. They're not like a Gaussian at the origin or something like that. Okay. Next. You can work out the Hamiltonian by doing this, thank you, by doing this thing where you, you work out the canonical momenta and you do, pi x dot, h equals pi x dot minus L, where that's L. Okay? If you do that, what you find is that h is 0. Okay? That should make sense because it's topological. There's no energy really. Okay, so h should be 0. This should feel right. What this means is all states have 0 energy. Okay? All right. And now, let us now construct the space of operators that act on the states. Okay? Now, what can we construct? The space of operators has to be gauge invariant, which means that basically the space of operators is those two things. Okay? But now we've made a certain choice about space, all right, which means that not everything works, all right? So the only non-trivial quantum operators are W, I'm just calling it W because there's only one of them, which is the integral over S1, it's this S1 factor, okay? The only S1 we have times A, and G, which is the integral S2 over the only S2 that we have, okay? So these you should view as quantum operators, okay? So these now act on the Hilbert space of states. Now it looks the same as that, and it's sort of, it is the same thing, of course, but the interpretation is a little bit different because we view those in Euclidean in a path integral formulation, and these we're viewing as operators which act at a fixed time on a fixed time slice, okay? Now, yes?
So these are very particular choices of the spatial part.
Yeah.
Could you choose something else or also something non-compact?
If you choose them as non-compact, then it becomes a bit complicated because the Hilbert space depends sensitively on what boundary conditions you put at infinity on the edge of the non-compactness. And you can probably think about it, but it does, there's different ways to terminate your Chern-Simons theory or your BF theory on the edges, and they give you different states. So it becomes harder, but you can think about it, yeah. But I will not do that here. It's a good question, yeah. Yes?
I have a bit trouble thinking of these operators working on the states because if
Yeah.
the states are ground states, in what way could they change the states?
Very good. That's an excellent question. It's totally fine to change the state from one ground state to another ground state. It just means that it's a bit more restricted than what we're used to, but it means, for example, it might mean that you have multiple ground states, okay? And you go from one ground state to another ground state. So I now have to prove to you that there are multiple ground states, and these operators will act in that restricted ground space of states. That's what's going to happen in a second. Yeah, that's exactly the right question to ask. Yes?
Given that this is a topological thing, so you
Yeah.
don't have a metric,
Yeah.
how can you make this distinction between space and time?
The truth is, you can always make the distinction. It's just that your answers shouldn't care about how you do it. That's the real statement, okay? In this case, it's quite natural to make time the only non-compact dimension, okay? So, but for example, if you also had, time being compact, then for example, the partition function on S1 cross S1 cross S2 should be the same if you quantize this as time or as this as time, right? You have to get the same answer, and that's quite non-trivial, actually. To be honest, that actually happens even if you don't have topological field theories. If you just have conformal field theory, you also get the same sorts of non-trivial constraints, yeah.
And why do you have to make these choices for the manifolds that you integrate this on? Because for instance, you could integrate B on like the S1 cross the equation of the sphere or something like that.
No, excellent, good. Let's think about what happens if I integrate B on the S1, which is special, it's a non-contract cycle, times the equator of the sphere. So let's imagine that we try to unite these two and integrate B on this manifold, okay? Now, the point is that dB equals to 0, okay? Which means that whenever you define this on any manifold, you can continuously contract it, right? And you get the same operator when you satisfy that constraint. Which means you can take this operator and continuously contract this sphere until it falls off the top of the equator into nothingness and goes away, okay? So this manifold is contractible, which means this thing can have no action on the Hilbert space of states because dB is equal to 0. The only chance of getting a non-trivial operator is when you wrap a non-contractible object, so you cannot collapse it to 0. Okay? This is an important point, so let me just stress this. You can only define useful operators for topologically non-trivial cycles. This is a very good point. That's why I picked this to be S1 cross S2. I wanted to have one interesting 1 cycle and one interesting 2 cycle. That's the only reason why I picked this. Okay, excellent questions. You are all anticipating amazingly what I'm trying to say, so this is perfect. Okay, good. So now that we have some operators, we want to compute their commutators. Okay, what is the algebra of these operators? And again, we do this in the normal way. So let's take a second and look at that thing. Notice that, the way in which we normally do quantum mechanics is you find the canonical momenta by taking the derivative of the action with respect to like the field dot, right? Like the momentum conjugate to A is dl dA dot, okay? If you look at that and think about it in components, dl dA dot is B and dl dB dot is A with some indices, right? In other words, B and A are conjugates in the quantum mechanical sense, okay? And what that means is this thing should have a non-trivial commutator, right? Because A and B are commutators. Okay. And now you work that out using the normal formulas. What you find is that GW, let me erase the hats just because I think they're aesthetically unpleasing. GW is equal to e to the 2 pi over n WG. Okay? This follows from a few lines of algebra that you can happily do. This is really a genuine exercise. Okay? This is, of course, the same as that linking relation, right? If you cut open the linking relation, you can derive this as well. It's the same. It's all the same thing, expressed in many different ways. Okay. So now this is a certain algebra of operators, and now we seek to realize this on the space of states. Okay? And now the first thing I want to point out is that this algebra, you cannot realize this on a one-dimensional space of states. Normally you have a unique ground state, but this means that you can't have a unique ground state, right? If you had a unique ground state, you could act with this on the unique ground state and get the unique ground state again, and you could act with this on the unique ground state and get the unique ground state again, and then you have the unique ground state equals to a phase times the unique ground state, and that's bad. Okay? So this algebra immediately means that we need to have more than one ground state, and the lowest dimensional representation, the simplest one, so the simplest rep is n-dimensional. Okay? And I will label the states by ket n, where n is in 0, blah, 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 up to n minus 1. So little n is a number that runs from 0 up to capital N minus 1. And the states act in the following way. W acting on the state n increases n by 1. Okay? Where I wrote that a bit too enthusiastically. It increases little n by 1 mod n. Okay? So you go around the clock, and if you go all the way up to capital N, you go back to 0 again. And G acting on n is the exponential of 2 pi I little n over big N acting on the state n. Okay? So just to stress, these n states are eigenstates of G. If you act with G on the state, you get the little n raised, as a phase. And W acts like a raising operator on n. Okay? And now you can check that this satisfies that algebra. Okay? Just evaluate both sides of this on each of the n states, and you'll see that, for example, acting with this on the left, you get the thing plus 1, then you measure that phase. Acting on the right, you first measure the phase, then raise the state, then get the extra plus 1 from there. Okay? So it works out. Okay. So note that we have n states. And we have them because of the non-trivial topology. In particular, if we had played the same game on S3, then we would not have been able to construct non-trivial operators, W and G, and we wouldn't have had them, we wouldn't have had to represent them in this manner. So you only get a non-trivial ground state degeneracy if you have some non-trivial topology. Okay? So this is one of the hallmarks of topological order, that on a manifold non-trivial topology you have degenerate ground states. Does that make sense to everybody? Okay. Now, physically, what are these things? You know, what's happening physically? So you can get an intuition for this by looking at what W is doing, right? You see, W is there's a number n, and acting with W increases that number, right? So physically, what these things are is, my spatial manifold is like S1 cross S3, right? Sorry, I keep saying that. S1 cross S2, this is my spatial manifold. And what's happening is that the action of the operator W creates a string, creates a flux tube or something like that on the S1. That's what W does, okay? Little n measures the number of flux tubes that are wrapping this S1. So we can have 1, 2, 3, 4, but then when we hit capital N, it becomes trivial again, and then they all vanish. Okay? So that's what W is doing. W creates a flux tube, and G measures the number of flux tubes that are piercing this thing, okay? Which is, of course, if you look at the geometry, is the same as the number of flux tubes that's on S1. So G creates a flux tube, and G counts them. Okay? Yeah?
So can you define some kind of joint in this space, like a lowering operator that removes the flux tube?
Yeah, I mean, W dagger removes them. Yeah, it's nice like that. Yeah, this is simple. It's not like okay, I guess that's always the case. You can always take the dagger and it has the opposite action, but here it's simpler. Yeah, exactly. You can also just act with W n times, and you know, and n minus 1 times, and you'll also get 1 less. Yeah, exactly. Okay. All right, so this is another example of topological order. This is always what's happening in topological order. You can create some extended object which wraps something. Okay, there's a lot more to say about topological order. I just want to make a few remarks before we'll take a brief break and then switch gears. So I just gave you this using the Zn case in 4 dimensions, but you should be able to see how to generalize this to any number of dimensions, right? Just change the A1 and B2 to like AP and BQ. You know, you get the idea. By now, I claim you are now qualified to discuss using this action, the spontaneous breaking of a Zn symmetry for any P form in any number of dimensions, right? Everyone can do that. Okay. The simplest case is not this one. I just presented this one because it's the one that's relevant to non-abelian gauge theory. The simplest case is the Z2 case in 3D. All right. And remember during the tutorial last time I drew a picture of some phase diagram for Z2 gauge theory? That BF theory describes the interior of that phase diagram. What I call the topological phase, it's described by this. Okay, it's described by that theory with a 4 equal to 3 and n equal to 2. Okay? And there's a very simple, these things that I just showed you, this commutation relation and so on, it turns out there's a very beautifully simple realization of that. It's something called the toric code. Okay, due to Kitaev. The toric code is a Hilbert space realization of this stuff. Okay? It's nice because it's really very simple. You have a bunch of spin halves on a square lattice, and you get all this stuff in a really simple concrete model. So I recommend that you take a look at that if you're interested in this. And now I want to also make some contact with the other set of lectures that we have on entanglement entropy. So you might ask, is there a connection between topological order and entanglement entropy? And it turns out that there is, okay? So let's consider computing the entanglement entropy. Let's do it in a 3D system so I can draw a simple picture, okay? So let's compute the entanglement entropy of a disk, of a 2D disk in some 3D theory, okay, that has topological order. So in other words, what I do is I take my region A, okay, and this is a two-dimensional disk in the vacuum of some three-dimensional theory that has topological order, where by topological order I mean exactly this, that it spontaneously breaks a one-form symmetry. Okay? Now, it turns out that that has an imprint on the entanglement entropy, and let me explain to you why. You see, when you have a higher form symmetry or one form symmetry, it means that there exist strings that can't break. That's really the whole point, right? And so there are these strings that are moving around in the vacuum. Okay, the vacuum is full of strings that are doing their thing and they can't break. Okay. When I say the vacuum is full of them, that's because if you act with this operator W that creates them, it has no effect because it has a perimeter law. And that means they were already there in the vacuum. The vacuum is full of a sea of these strings moving around. Now, there's something interesting that happens here, which is that the vacuum is full of a sea of closed strings, okay? In particular, this cannot happen. Every string that enters must leave. And that means there is a reduction in the entropy of this region, right? Because you know that every string that entered has to leave. That reduction is called topological entanglement entropy. All right, and what does it mean? So as you know, if you compute the entanglement entropy of the disk, what you find is there's going to be some sort of short distance divergence, right? This area law, which goes like the radius, it goes like the sort of the edge of the disk. So in this case, it's going to go like 2 pi r divided by some UV cutoff. So this is a UV divergent piece, okay? But then there is a reduction coming from this higher form symmetry. And in the case of the toric code, which is the only case that I've worked out carefully, it's log 2. And in general, it would be log n, okay? So this is capturing the idea that closed strings that enter have to leave again. Okay? And you can prove this in various ways. You can do it from this Hilbert space realization, okay? But you can also use the techniques that we have learned from Nela's lectures. Let me sketch how you would use those. To compute an entanglement entropy, what you do is you create some sort of replicated manifold, right? You make n copies, create them with a replicated manifold, and compute the partition function on that replicated manifold, right? So you can imagine doing that here, okay? Take many disks, create these branch cuts, sew them together, and then that gives you, eventually you sew it back again, and that gives you some sort of complicated three-dimensional manifold with some topology, okay? Then you evaluate that partition function coming from that action on that non-trivial topology. That gives you some sort of answer. And then you come back and you digest that answer and you find that it has this UV divergence minus this thing coming from there. Okay? That's another way to calculate that. Okay. And the last thing I'm going to say about topological order, I'm just going to do something terrible and just squeeze this into this spot here because I don't want to erase the board before the break. Is just to say that the example I gave you, I think, is in some ways the simplest, but it's not the canonical example of topological order. The canonical example, so the earliest discovered, so maybe the earliest, is what's called the fractional quantum Hall state. Okay, this is another example of topological order, and it's a lot like this. Okay, what you do is you take some magnetic fields, you put them in some very strong. Sorry, take some electrons, excuse me. And then you put them in a strong magnetic field, all right? And then it turns out that there's some sort of emergent long-distance physics, which is described by the following action. IK over 8 pi A wedge dA, okay? So what's happening here, you see how I just sort of made up some gauge fields to realize my symmetry? You could say that those gauge fields are emergent. In the same way, this A here is an emergent gauge field that describes the long-distance physics of these electrons in this magnetic field, okay? And there's some non-trivial topological order describing this. It's really quite similar to what this theory just described, except that notice that it's the same gauge field twice instead of two different gauge fields. that means that some details are a little bit different, okay? And that's quite important, but philosophically it's the same. And just as, here what I did was I started with the non-abelian gauge theory, I showed you there was some symmetry, and then I tried to realize it in a minimal way. You do the same thing with the electrons in the magnetic field, but it's a little bit harder because it's very strongly coupled always, okay? But you can do this, and this is, I think, the first example of topological order. This is a beautiful story. I recommend David Tong's lecture notes on this if you're interested in learning more, okay? Okay, we are at 2:15, so I think that now we should take a break and maybe come back in, let's say come back in 5 minutes. Is that okay with us? Come back in 5 minutes for the last chapter of this. Okay. Come back at 2:20. Okay. All right, everyone. Welcome back. So we're now moving on to what is the last chapter, the last topic that I'm going to discuss. And these are finally the famous non-invertible symmetries that I told you I was going to talk about all this time. Okay. So this is a relatively new topic, actually. And let me now explain what's going on. So this is the final section, non-invertible symmetries, which I'm going to explain using what the example of it that got me into the fields of non-invertible symmetries, which is the ABJ anomaly, the Adler-Bell-Jaquiev anomaly. All right? Okay. So let me just put this in context. All of this time, we have been discussing symmetries that have a group law, right? In particular, we've had some sort of topological defect labeled by some element of some group, and then, we had something else. So let me just call this M sub p, and some other M sub p, and it was always the case that we could fuse these together in the following manner, okay? So in other words, if I have some guy living on some manifold, and another nearby guy, this is generating action G, this is G prime, I can always fuse these together and just get one more object. Okay, I fuse them and get one new symmetry generator, which is labeled by the group composition of G and G prime. This has been the case in the very first symmetries that I talked about on the first day, and it was even more the case for the higher form symmetries, because these G's then had to be abelian. Okay, so it was really a trivial group composition. But, I'm sorry, what that means in particular is that if you take U of G, then by the properties of groups, there's always something like this, U of G inverse, that undoes the action, right? There always exists G prime such that this is possible. You act with UG, you act with, sorry, not G prime, there's G inverse such that this is possible. You act with UG, you act with UG inverse, you get 1 back again, okay? But, once we have realized that symmetries are created by topological objects, you can ask, is this the most general case? And, I mean, it's not, right? You could imagine something like this, that you have symmetry operators that are labeled by some index A, where A doesn't run over a group. It just runs over some set of things, okay? And then you compose them, compose 2 of them, where A runs over this set. And what you get is not just a new element of this set, but rather some sort of a sum over elements of this set. Something like this. Okay? Where NABC is some set of numbers that's determined by your theory in some sense. This is a generalization of that because, A, B, and C are not in a group necessarily. Okay? Clearly, you can choose NABC so that a group is a special case. If these guys are all mostly 0 or 1, then that will happen. But you could have it so it's not in a group in this manner. All right? But viewed as a fusion of topological objects, this is completely fine. Right? Not only is it fine, it's known to happen in some theories. For example, if you write down non-abelian Chern-Simons theory, then you have Wilson lines in that theory. And the fusion of those Wilson lines, first of all, those are topological objects, and their fusion is like this, with some numbers n, a, b, and c that you can calculate. Okay? So this is quite a reasonable thing to think about. And from the point of view of these lectures, I've been emphasizing that symmetries give you topological defects, And I've been stressing that we should try to invert this logic as well. The topological defects can be thought of as being some sort of symmetry action. So from that point of view, this is an example of something which might be called a non-invertible symmetry, right? You can easily, let's set this up so that there's no way to undo the action of a symmetry operation. In other words, there will never exist some choice of A, B, and C so that you get 1 on the right-hand side, but it'll still be a topological defect and therefore can still constrain your theory. Okay? That's the idea of non-invertible symmetries. Now, I'll be honest that I did not realize quite how powerful this idea was. What really changed my mind on this field was when some authors in 2022 used this to understand the Adler-Bell-Jaquiev anomaly. So I'm now going to explain that story to you, because I think it's really a beautiful application of this formalism, because it takes something that we sort of all know about and sort of casts it in a new light, and you realize that there's a really beautiful way to understand it. That's now what I'm going to do. Any questions about the philosophy before we get into the ABJ anomaly from the point of view of, yeah? What the sum inputs, meaning these NABC, or? You want to, sorry, I think I didn't understand the question.
If you just have the sum on the right-hand side, I can't tell which pieces have been going into the sum created in the first place. And that quite invertible?
I just mean it's not invertible in that there is no, if you act with UA, you might not be able to find a UB so that you get 1 on the right-hand side. That's what I mean by non-invertible. Okay, like, there's some algebraic property of this, right? If ever it's the case that you have more than one thing on the right-hand side of this, then generically you can't invert it again. That's what I mean. Like, this won't happen, okay? And you'll see a very concrete example of this in a second, that there'll be an action you can't invert. You can, yeah, basically the answer to your other question, which is, do you know what A and B went into it? That depends on the properties of this matrix, right? And you can look at it. I don't know the answer of that, to that question immediately, yeah. Good, yeah?
I came across categorical symmetries.
Yes.
This is the same thing because it looks the same.
Yeah, the word categorical symmetry is used in many different ways, to be honest. I think nowadays it's converged to mean that, basically. I think that's correct. Do you agree, Pablo, with that statement? Or okay, I don't want to push you on the spot, but yeah. Oh, it's just the word categorical symmetries has been used in many different ways in the literature. I believe in the recent years it has converged to be equivalent to that statement. Do you agree with that? Yeah. Okay. That's right. Yeah. So yeah, but I think it basically means this. Yeah, that's right. The right language to the right math for this sort of thing is category theory, I believe. But I don't know enough about that to give you a good lecture on it, so I'm not going to. I'm going to tell you about the physics applications of this. Yeah.
It wouldn't, even if it was invertible,
Yeah.
it wouldn't really necessarily be even a group because it doesn't even have to be closed in the sense that there is no one single element on the right, but more generally a sum. If I'm understanding it correctly.
Yeah, that's correct. One should think carefully about the interplay of these two things. If you have a sum, then it's already not a group. That's right. Yeah, it's already not a group. Some of the most interesting cases always involve this thing actually being non-invertible. So yeah, yeah, that's right. Good. The sum already takes us outside the group language. Yeah, that's right. Good. Okay. So now what we have to do is first remind ourselves briefly of the different sorts of anomalies. Yeah. Okay. So different types of anomalies, and I have to do this because I want to explain what I'm calling an ABJ anomaly exactly. All right. Okay. So I want you to consider the theory of a Dirac fermion. Okay. And I want to couple this Dirac fermion to an external source. Okay. So here I have my Dirac fermion, and this is an external source. So the fermion is dynamical, but this is fixed and external. Okay? And the action is the following thing, d4x psi bar d slash minus iq, sorry, I'm going to set a to 1, set q to 1, minus a slash psi. Okay, it's a unit charge Dirac fermion. All right. And sorry, it's important that it's massless. Okay, it's a massless Dirac fermion. Okay. M is equal to 0. All right. Now, what are the global symmetries of this theory? This action looks like it has two global symmetries which act in the following way. Psi goes to e to the I alpha over 2 times psi. There's a reason for the over 2. and psi goes to the ei alpha over 2 gamma 5 times psi. Okay, so there are two classical symmetries. This one is called U1 vector, and this one is called U1 axial. All right, and A couples to the vector symmetry. All right, I've coupled the external source A to this symmetry, not to that one. All right. And I really have not been using this board well. Let me write this a bit more aesthetically. This has a current vector. So this is U1 vector, which has a current, which is psi bar gamma mu psi. And similarly, this is the U1 axial symmetry, who has a current, which is psi bar gamma mu gamma 5 psi. And I have coupled A is an external source for the vector symmetry, okay? Not for the axial symmetry. You can see that this formula right here is A mu, gamma mu, and so therefore it couples to the vector symmetry, okay? This is normal QED stuff, except that I'm holding A fixed, yeah. Yeah, you can do that. You can do that. Indeed. This is what I'm going to tell you is a subset of what you get if you couple in a source for both the axial and the vector. You can definitely do that, yeah. I'm just setting that source to 0 for writing down shorter formulas, to be honest. Okay? And this is the vector current and the axial current. Okay? So people have seen this, I think. Okay. Now, this is a symmetry of this action. However, it is not a symmetry of the quantum theory. Right? So famously, if you take this action and you throw it into a path integral, so make a path integral. So if I construct z of a, all right, which is the path integral over d psi bar of e to the minus this action, okay, so if I throw this into the path integral, then this axial current is not a symmetry of the quantum theory, okay? People have heard of this, is that right? People have done this. What you do is you calculate some sort of a triangle diagram that looks like this, and then if you have the axial current here, so this is J mu axial, and you have some vector current insertions here, then there's a thing where this diagram should be 0 if you compute the divergence of this, but it's not 0 for deep and cool reasons. And what you find is that the axial current is no longer conserved. In particular, in the quantum theory, you have that d star J axial equals to 1 over 4 pi squared f wedge f, where little f equals to d of little a. Okay? So this is the triangle anomaly. Triangle diagram. Okay? So you compute this diagram and you get this. Now, I want to stress that in this expression right here, this part here is fixed, right? It's a fixed external source, so you can make this whatever you want. Because my only dynamical degree of freedom is psi. I'm not making a dynamical. All right? So when you have something like this, where the right-hand side of a symmetry current, of a quantum operator, the divergence is not 0, but is instead a fixed function of the sources, this is what is called a 't Hooft anomaly. Okay? And from the point of view of predictive power, of being able to say things about the theory, a 't Hooft anomaly is good. Okay? Because typically when you have a theory of 't Hooft anomaly, you can say more than you could before. All right? So 't Hooft anomaly, despite the sort of negative connotation of the word anomaly, a 't Hooft anomaly is a good thing. You can say more than before. All right? So for example, to give you an example of the sort of thing that you can do, you see, a theory with a 't Hooft anomaly can never be in a phase where the theory is completely gapped with a unique ground state. And the reason is that, imagine that it was completely gapped. Okay, there's a mass gap. Nothing is happening below some scale. Well, what I can do is I can create a very small field here, because I control this one, right? I can make this whatever I want. I can make a very small field here, and then that will start to create some particles. That's what this means, right? This means that the fields here create particles from nowhere. But if the theory is gapped, then I shouldn't be able to do that. This is then constrained by dynamics, and this is not. And that would be a contradiction. So whenever you have a 't Hooft anomaly, you know you can never have a trivial gapped vacuum. Okay? That's an example of the kind of thing that you can do. So 't Hooft anomalies are cool. Okay? They're good things. Now this is not what I'm going to talk about. Okay? This is very extremely well understood. I'm going to talk about something a little bit different. All right? Do I want to do this here? I think I do. Or, okay, no, I'll do it on the next one. All right. So I want to consider now not this theory, but a slightly different theory. I want to now consider the theory where A is dynamic. Oh, sorry, thank you. I want to now consider the theory where little a is dynamical. Okay? So I want to now consider making A dynamical, little a. So I'm no longer considering the massless Dirac fermion. Instead, I'm really considering massless QED, right? So in these lectures, I've tried to make the external sources lowercase and the dynamical fields uppercase. So now I'm no longer it's no longer little a, now it's capital A. This is a dynamical field. Okay, A fluctuates. And I'm going to now consider the following action. I have to give a kinetic term now. And the action is this. Oops, there's no I there. There is an I here. Where F equals to dA. Okay? And in my partition function now, I'm going to path integrate over both fields. Okay? So I integrate dA and over d psi. Okay. Now let's revisit this theory and ask, what are the global symmetries of this theory? Okay. So we know that there is a one-form symmetry for the magnetic flux. We know this to death by now, right? So there's the one that's like epsilon, mu, nu, rho, sigma, f, rho, sigma. That's there because there's a theory of E and M, and so that's there. Let's not stress about that for the moment. What happened to the axial current? Okay. Well, the axial current equation, the equation is still the same, but now it has a very different character, right? The right-hand side of this is now a dynamical operator. It is not a fixed external source. Okay? In other words, we can't control this anymore. Now this operator will just do what it does. It might fluctuate, it might not. It will just do what it does. And that gives this a very different character, this anomaly. Because now it looks like the divergence of the current is just something, right? It's just some other random operator. And I mean, typically in life, when you have a current and its divergence is just something, you don't call that a symmetry, you just call that a vector field, right? I mean, you know. So this looks like it's much worse than before. And this thing is called, I'm going to call this now the Adler-Bell-Jaquiev anomaly. I'm going to call this guy the ABJ anomaly to distinguish it from the 't Hooft anomaly over there. Okay? This notation, by the way, is really not perfect. Many people used to use ABJ to mean anything with a triangle, which didn't distinguish between these two cases. By now, it seems like the literature has settled on this, that the ABJ is the dynamical one and the 't Hooft one is the fixed one. But okay, that's what I'm going to do. And just be, when you're studying this, just make sure you know what kind of thing you're talking about. Okay. Okay. Now, our goal now is to make sense of this object, okay, to see what to do. Now, this is really genuinely a tricky problem, okay? I got into this field because I wanted to develop a hydrodynamic theory for this thing at finite temperature. And hydrodynamics really involves the global symmetries in some deep way. And you see, this is perplexing because, you see, it doesn't feel like you've lost the symmetry completely. It feels like there's something special happening here. But for a long time, I could not characterize exactly what the specialness was. I mean, you know, it's just an operator, you know. So what you really want is some way to characterize how is this different from just breaking the symmetry completely, okay? And it is different, and now I'm going to show you how to think about the fact that it's different, okay? Are there any questions philosophically before I get into this? Do you understand the goal? We want to understand this in a precise manner now, okay? Okay, So let us now try to make sense of the ABJ anomaly. Okay. All right. So yes. So the first obvious thing to try to do. Okay. So our goal now. Goal, make sense of this. And okay, there's a first kind of obvious thing to do, which everyone tries, okay, which is, let me define a new current, which I'm going to call star J A twiddle, okay? Star J A twiddle is equal to star J A minus 1 over 4 pi squared A wedge F, okay? All right, this seems like a good thing to do, because if you compute d star J A twiddle, you get 0, right? Because d star J A twiddle is equal to d star J minus d of this, which is minus F wedge F, right? So therefore this bit cancels out the offensive bit from there and you get 0, okay? All right, this sounds good, but however this does not work, all right? Because J A twiddle is not gauge invariant. Remember, A is a dynamical field with a dynamical gauge redundancy, and things that are not gauge invariant don't actually exist. They're just fictions of our imagination. All right? So we cannot work with this current. Okay. So we could now just try to make sense of this. You see, it looks like the gauge variation of this is like d lambda wedge f, which is a total derivative, right? So if we just integrate this over something, then maybe we'll be okay. So let's try to do that next. Okay, let's integrate this. We don't have a current, but we might be able to get a conserved charge, which is, for some purposes just as good. So let's try to do this. Let's ignore what I just said and try to construct the following object. So we're going to integrate this, and I'm going to also exponentiate it for a reason I'll show you in a second. So here's an idea. What we can do is we can try to integrate this over in the following way. Okay. So what am I trying to do here? I'm trying to create the object that generates a finite rotation. Okay? So this thing in here is what we normally call the charge, and I'm exponentiating it with an amount alpha. This is what I did earlier, right, for normal global symmetries. Now I'm just doing it for this ABJ anomaly thing. Okay? Okay. Let's look at this guy. This is a candidate charge generator, right? Okay, so what are the things we need from this for this to successfully work? First of all, we need this thing to be topological with respect to M. If I wiggle M a little bit, I want it to not change. That will happen provided D of the thing on the inside is 0, which it is. Okay, okay, so good. This object is topological. All right. Now, is it gauge invariant? Well, let's look. It is actually gauge invariant, right? Let me explain why. So the integral of A wedge dA under a gauge transformation where A goes to A plus d lambda, this object goes to d lambda wedge dA, and then by integration by parts, I can take this and move it over there. So this is actually 0 because it's integrated. Okay? Okay, good. So it's invariant, it's gauge invariant under small gauge transformations. Under small gauge. But now you see where I'm going with this, right? Is it gauge invariant under large gauge transformations? Under gauge transformations where I allow this thing to wind over some non-trivial cycle. So say I make M3 be some non-trivial manifold, is it gauge invariant under those? And the answer is no, right? Remember we did this problem like a day ago, right? I wrote down a Chern-Simons action. I said gauge, what does large gauge transformation do? And what that does is that quantizes the coefficient of the Chern-Simons action. In other words, it's only going to be gauge invariant under large gauge transformations if alpha is some quantized value, right? So what do we get? If you go through it, it turns out, no, failed. Okay. Yeah. It turns out that this is gauge invariant under large gauge transformations only if alpha is in 2 pi times the integers. Okay. Now, this is actually very bad because you see alpha is a rotation angle. If alpha is quantized as 2 pi times an integer and it's a rotation angle, then that sounds like it's really not working. If you go through the factors carefully, it turns out if you have an object with axial charge q, so if you have OQ, this thing rotates that guy by e to the I q alpha over 2, okay? Which means that if q is an integer, which it is in my normalization, then at best what you can do is flip the sign of O. If q is odd, this will flip the sign of O, which means we get a Z2, which is not great. I want it to get a continuous symmetry, okay? The Z2, by the way, so that's Z2 that you get. So basically, a Z2 survives, and that Z2 acts on the fermion field as psi goes to minus psi. So it's basically fermion parity, okay? It's great, but it was not anomalous to begin with, to be honest. So it's not, you know, I want more than this, okay? Okay, so this is bad, okay? We have no continuous symmetry. And this is where this field stood for a long time, I would say, until 2022 May, when 2 papers explained the right way to think about this, which I'm now going to explain to you. Okay. Any questions? Does everyone understand what the problem is at this point? Everyone happy with the fact that something is wrong? Yeah, okay. Some people look something is wrong. Yes. Any questions? Yeah.
So this isn't a problem if your space-time is topologically trivial, right?
Yeah, that's right. So here's one thing you could try to do. You could be like, all right, fine, this doesn't work on some fancy cycle, but let's not worry about it. Let's just evaluate things on all of R3. I'm going to look at conserved charges on R3 and not worry about this issue at all. Okay, and that's actually fine for some purposes. Like for example, you can derive selection rules on amplitudes like that. That's okay. But truth is, it's a little worse than it sounds because non-trivial topology appears in other ways. For example, if you ever have on a 't Hooft line creating a magnetic monopole, then that's basically non-trivial topology because things don't exist where the 't Hooft line is, and that also will cause problems for you. And so again, you can choose to not worry about monopoles, but now you feel like you're missing something because the monopole operator, the 't Hooft line, is the object charged under the actual global symmetry of the theory, this one-form symmetry. And now you feel like you're missing something. And yeah, so that's the thing. Yeah. And yeah, and you are. Yeah. So I'll now explain how to make sense of this. Yeah. But I should stress that you can get pretty far. I mean, you might feel like you're missing something, but you can get some constraints. So it's not the end of the world. Okay. Good. So now I'll tell you how to make sense of this. All right. And we're going to first solve this problem only for a specified set of rotation angles, okay? So let me consider rotation angles that are like this. Okay, so this, by the way, is the solution, and this is from 2022. And what you do is you consider rotation angles, alpha, that are of the form 2 pi over n, where n is an integer. Okay? Let's try this, see what happens. Okay? Now, for the reasons that I just said, this operator does not exist. okay, for any n greater than 1. But let's consider a different thing. Let's consider so what I'm going to do is I'm going to make up a new field. Okay? I'm going to call it B. B lives only on M3. Remember, I'm defining a topological defect, which means I'm defining some submanifold, M3, a codimension 1 submanifold. B lives only on M3. I'm going to integrate over B. I'm going to define the following thing. Okay. So I've done something radical. What I've done is I've made up a new field B. It's a new U1 gauge field. It's a new U1 compact gauge field B, and path integrated over it. I stress that B lives only on M3. So it lives only on the defect. Okay? And I've path integrated over it with a very specific action. Now let's stare at this action for a second. It's a Chern-Simons action for B. Of the sort that we've discussed earlier, it's B wedge dB. Okay? So this is a topological field theory action. I've also coupled B to my dynamical photon field, to this B wedge dA thing. Okay? And finally, the star JA is doing the same thing as before. It's the same guy as from here. Okay? And the angle alpha that appeared multiplying star JA, this same angle alpha still multiplies it. That's why I have this ugly 2 pi over 2n structure. Okay? It's really 2 pi over n times half. Okay. Now, why have I done this? What am I doing with this? So the first thing I want to point out is this object is well defined. Okay, first of all. Let's just make sure it's well defined. Okay? The action for B, B wedge dB, has the n in the numerator. All right? Which means because n is an integer in the numerator, this is invariant under large gauge transformations, because n is on top, and that's what you want. Okay? A now appears only in this way, 1 over 2 pi B wedge dA. Okay? This coefficient is 1, so this is also fine. Okay? So all of this is fine. So this object is well defined under all gauge transformations you can imagine. However, let's now imagine taking this and eliminating B. Because B, we just made up B, right? Let's try to get rid of B and see what happens. The equations of motion for B are that if you vary respect to B, what you get is, let me actually just write this down. What you get is n over 2 pi dB equals to dA. Which means, so this is the equation of motion for B, which means that, well, B, that's better. Good. Now it's okay. Which means that B, I'm really messing this up here. It's a minus sign. Okay, I think now it's okay. Yeah. Which means that B is equal to minus A over n. I'm going to put this equal sign in quotes for reasons I'll explain in a second, but if you just don't think about it too hard, you get this equation. Okay. And now if you take this and plug back into the action, this action here, what you find is, let's just look at the n scaling of this term. B goes like A over n, dB goes like A over n. I have n times A wedge dA over n squared, and it turns out to be exactly this guy with the n in the denominator. Okay? So in other words, by introducing this new field B, I have created the action I wanted, which I said earlier was ill-defined. I've created U alpha, okay, in a well-defined way, somehow. All right. In particular, this object is a topological operator that rotates local objects, local operators O, by O times e to the 2 pi I, hang on one second. As e to the 2 pi iq over 2n for any n. So I can now generate a fractional rotation of the full circle for an as fine of an angle as I want. Okay? The cost of this was that I had to introduce a new field. But the field, it doesn't live everywhere. It only lives on this codimension 1 surface. Okay? So in a sense, what I'm telling you is that to count the charge in this theory, you can't just count it. You have to sort of introduce a new guy, B, who does the counting for you, and he kind of runs around, looks at the magnetic field lines, and so they're doing something, and he does the undergo. At the end of the day, he counts it for you and tells you what the charge was. Okay? You can't just count it in an obvious manner. All right. Okay. Does that make sense to everybody, what just happened? So this is the right way to think about the Adler-Bell-Jaquev anomaly. There's a topological operator, but it introduces a new object, and I'm about to show you that it's actually a non-invertible symmetry. So I'll show you what that means in a second. Okay? Now, I feel obligated to tell you, this is a sleazy equation, all right? Because you see, if you take d of this equation and then integrate it over some non-trivial 2 cycles, then it doesn't actually make sense exactly because the n is in the denominator, all right? So the truth is, this is not really, this gives you the right answer, but it's not really a good argument, what I just gave you, even though it's a quick one. The right way to do this is something different. I'm going to tell you in words the right way to do this, and this was done in the papers by, that I'm citing there, which is Shuheng Shao, Eugene Choi, and also Kantaro Omori and Clay Cordova, and sorry, Hotat Lam, I left out that name. And what they did was, you imagine you have this one-form symmetry for the magnetic field lines that I kept talking about. You take that one-form symmetry, and in half of the space, you gauge a Zn subgroup of that one-form symmetry, okay? In half the space. The boundary where you stop doing that is a topological place, and that boundary, the topological boundary, turns out to be given by this action, okay? Okay. That's the more formal way to do it, but this gives you the right idea. Okay. Now, what else did I want to say? Okay. So now I want to sort of explain to you why this is non-invertible and what that means. Okay. So to see that it's non-invertible, okay, I'll need more board space. Oh, okay. I'm doing all right. Any questions while I erase the board slowly? everyone happy with this? Normally people are unhappy with this, so. What?
They're not gauge invariant, right? They're invariant under particular Zn subgroups.
No, these are totally gauge invariant. Yeah. They generate a Zn subgroup of the axial rotation. So maybe I'll explain that a bit later. What they do is when you act with them on a fermion operator, they multiply it by an axial phase that forms a Zn subgroup of the U1. Okay? But they're completely gauge invariant. Yeah. They have to be completely gauge invariant because otherwise they would be terrible operators. Yeah.
So this rotation angle isn't the gauge parameter.
Nope. This is the axial charge rotation parameter. Does that make sense? Because the axial charge is a global symmetry, or trying to be a global symmetry. Yeah, it's that parameter. Yeah. It's the one that, it's the e to the I gamma 5. E to the I alpha gamma 5, yeah. Yeah, please.
And something with the overall picture.
Yeah.
So is this now the thing we constructed somehow the quantum analog of this axial symmetry?
Yeah, exactly. The thing that used to be the axial symmetry doesn't quite work anymore, but now you have this new object which still implements the axial rotation on charged operators. I'll write down a formula for that in a second. But yeah, exactly. This is the thing that used to be the axial symmetry in the classical theory. This is the quantum version of the axial symmetry. Yeah. That's, I think, exactly the right way to think about it. Yeah. Yeah. Okay. Okay. All right, so now just to say in words again, write down the formula again. So just to stress what just happened, I have created a topological defect, d1 over n, which lives on 3 manifolds. It's a topological defect. It's labeled by an integer n and, labeled by an integer n, and it generates an axial rotation by an angle 1 over n. Okay. Now, now let me explain what I mean. So this, as you just pointed out, this is basically the quantum version of the axial current. Okay. In the quantum theory coupled to dynamical QED, this is the best you can do. Okay, sort of. This is a thing you can do. And the way we got this was by introducing a new field B, which lived only on the defect. So now I said this was not invertible. Let's understand why. Let's try to imagine doing a rotation. So this thing rotates all local fields by e to the 2 pi I q divided by, I keep messing up this factor, divided by 2n times O. So this rotates all local fields like this. If you wrap it around, if you drag, what that means is that you have this topological defect. If you drag a local operator through here with axial charge Q, it'll pick up this overall phase, okay? But now let's imagine trying to undo that. So let's imagine acting with the rotation 1 over n, and then the opposite rotation, okay? So what I'm imagining doing is I'm acting with a rotation angle 1 over n here, and then minus 1 over n. Okay, so I'm fusing these two things together. For a normal symmetry, if you rotate one way and then the other, you get the identity back again. Okay, it just gives you a 1. What happens here? So here, if you rotate this way and then back again, then I have to introduce on each of these defects, I have to introduce a new gauge field. So I have B1 on the first one and B2 on the second one. All right? So here we have B1, here we have B2. And now I imagine composing them. So I have somewhat stupidly, did I erase everything? It was dumb. Hopefully I kept the, yes. No, okay. Well, I erased the important equation stupidly. But you know what it was? It was there was a piece involving star J axial and then some Chern-Simons terms for B, all right? So the piece involving J axial indeed comes with the opposite sign and cancels, all right? But the other ones survive. So in other words, what do we have left? We have dB1, dB2, and now we have times the following weight in the path integral, the exponential of n over 4 pi b1 wedge dB1 minus n over 4 pi b2 wedge dB2 plus 1 over 2 pi b1 minus b2 wedge dA. Okay? So this survives, all right? Even though the part involving the axial current goes away. And this isn't trivial. This is not the identity, okay? This does something, all right? So in particular, you can imagine decomposing the gauge field into a sum of B1 and B2 and a difference of B1 and B2. And this difference field, B delta, couples to dA, which is the photon field. And so this is not a trivial topological defect. It's not the identity operator. All right? And so what this means is this axial charge rotation that I've constructed, though it's completely well defined, is not invertible. So the axial charge rotation is now non-invertible. This is now and this is non. Okay. So to answer your question, the quantum version of the axial charge rotation, the real way to say what the ABJ anomaly does is it takes the ordinary normal classical charge rotation and makes it non-invertible in the quantum theory. Okay, and this is the main point. Now, any questions about this? Yeah.
So, I mean, since before you said that if we consider topological trivial manifolds,
Yeah.
we could like ignore the Lambda
Yeah.
transformation.
Yeah.
But so I would expect that in that case now, this would give us the identity.
I think it doesn't give that identity. It just gives you a topological field theory that's kind of boring. That's all, because it's defined in a non, if you do what you just said and do it on a non-topologically interesting manifold, then you will get this non-trivial topological field theory, which is just, I wouldn't say it's the identity, but it's on a topologically trivial manifold, so it probably doesn't do very much. So maybe for everything of interest, it's the identity. So if that's what you meant, then yeah.
So if we had considered non-topological trivial, would have missed the non-invertible symmetry.
Yeah, I think that if you only look at topological trivial things, like you ignore monopoles and the 't Hooft lines, and only look at R3, then I think that you basically miss the non-invertible character. That's right. One important thing to note is that this thing that you get left over, it doesn't act on local operators. Okay, local operators, the local operator, you rotate them one way, you rotate them back. They're all happy. Local operators are happy. It is extended objects who get messed up by this thing. Okay, so if you need to look at Toft lines. So for example, okay, let me say two more things about this, and then I'll slowly start wrapping up. So one thing is, you might be worried that I only managed to generate a 1 over n rotation. Okay, now n is arbitrary. Okay, so I can generate a 1 over n rotation, and now by composing that over and over again, I can generate any rational angle, right? So I've generated 1 over n, and through math, I can do that p times. Okay, so really I can create a p over n rotation, which really means that it's any rational covering of the circle. Okay, so it's something like, you know, I don't know how to describe it. It's like the rational part of U1, whatever that means. Okay, it's not really a continuous rotation in the right way. It turns out you don't need to do the same. Doing it over and over and over again is really annoying. What you can do is you can just do it directly for a rational number by using a different TQFT, not the simple one that I wrote, and you can look at this in the papers. All right. Now, this does something. The fact that it's non-invertible means that it can do various things that an invertible one could not do. I'll just tell you one thing that it does. If you take this guy, okay, that I just introduced, and if you imagine taking a Toft line and dragging it through this thing, which you can imagine doing, right? Take a Toft line, it's a circle, drag it through this thing, then the Toft line acquires a tail. Okay? It ends up having a two-dimensional surface attached to it. All right? And this two-dimensional surface is basically the integral of f times 1 over n. And the way to think about this two-dimensional surface attached to it is that the monopole, you see the boundary of this surface is basically the integral of a, but not quite, because it's the integral of a with a fractional charge. And so what's happening is that this thing is attaching a fractionally charged Wilson line to a magnetic monopole. Those of you who have studied the Witten effect will find this very familiar. The Witten effect tells you that if you shift the theta angle of a U1 gauge theory by theta, then that takes every monopole and binds to it an electric charge with angle theta. And that's basically what's happening. And this is again expected on general grounds, but it sort of shows you this had to be non-invertible, because only if it's non-invertible can you do this non-invertible action of tying something to your thing. Okay? Okay, those are just some extra final words. But just to stress, there's a lot of stuff happening here. And again, there's more things you can do with this. We use this to prove a Goldstone type theorem using a slightly different thing, and you can look at all of that in the notes. Okay. Okay. Now, we are 5 minutes left. Okay. Now, in those 5 minutes, I want to tell you about some of my own work in this, which is a slightly different character. And the reason is that this has been, I've talked about some applications, but it's all been a little bit formal. But the truth is, I got into this field in a different way. I didn't get into this field in through a formal quantum field theory perspective. I wanted to describe some actual dirty systems. So I want to tell you about what my motivation was and tell you where that's going. Okay. So imagine that you care about the inside of the sun. Okay. So the inside of the sun has stuff going on inside of it. But what's really happening is the inside of the sun, it's described very roughly by electromagnetism, okay, coupled to charges. I'm just writing it like that. The charges here are, like protons, neutrons, and so on. But by this I mean charges, and this I mean electromagnetism. And the whole thing is at finite temperature, so it's all very hot. Okay. Now, say you want to have a hydrodynamic description of the inside of the sun. If you look at textbooks, there's a field devoted to this called magnetohydrodynamics, right? Which describes basically how magnetic field lines move around at finite temperature in there. Now, if you want to do hydro in the modern way to do hydro is the following thing. You look at the global symmetries, and you turn a crank that was taught to us by Landau, and those global symmetries should completely dictate the structure of the hydrodynamic theory. Okay? The basic idea behind this is that hydrodynamics describes long-distance behavior, And in a finite temperature system, if you make like a lump of an excitation, typically it'll just kind of vanish very quickly over some short time scale, okay, set by the mean free path or something like that, right? But if you make a lump of a conserved charge, then it can't vanish quickly, all right? Because it can't vanish, it has to spread out because it's conserved, right? So if in this case the time scale was very fast, so if omega was very fast, in this case the time scale will depend on the size of the lump. And as you make the lump bigger and bigger, it decays more and more slowly. So that means that at long times, the structure of hydrodynamics is completely dictated by the conserved quantities, which are themselves completely dictated by the global symmetries. So in other words, if you want to build a hydrodynamic description of this, what you should do is look at the global symmetries and then use them in thermal equilibrium the way Landau taught us to do. The thing that you've all learned here is that this system has a one-form global symmetry. That is the true global symmetry of this system. And you can now just try to use this to build a hydro theory and see what happens. And this is how I got into this field. We built this hydro theory, okay? And it's lots of fun, actually, because you see, the way MHD is normally done in textbooks is you write down this sort of thing, and then you build hydro for this, and then you couple it to this thing in some Maxwell's equation type way. But this is not quite what we did. What we did instead was write down the most general hydro theory subject to the symmetries and the principles of effective theory. Now, that includes this as a special case, but it's actually more general because it works even when the electromagnetic couplings here are very strong. It's also, in my opinion, a bit more systematic because you can really just enumerate all of the terms and so on and be very systematic about everything. You can systematically do effective field theory with it. And so we have a generalized global symmetries perspective on MHD. And recently, many of us are trying to push this in various different ways to see if this gives you some new perspective on I'm hopeful for real life, but in the meantime, there have been some recent numerical simulations that we've been able to explain using this that are very hard. I would say impossible to explain without using this effective field theory framework. Basically because in numerics, you can easily enter a regime where E and M is very strongly coupled because of lattice effects. And so this really helps understand that stuff. So the main point of this is that though in these lectures I've presented it from a sort of formal quantum field theory perspective, that is not really the point of this machinery. To give a sort of very brief summary of what we did, what we learned was that you can think about global symmetries as defining topological objects. Once you do that, you realize that you can easily generalize this formalism to discuss not only the symmetries for particles, but also symmetries for extended objects like strings, okay? And by strings, I mean things that exist in real life, magnetic field lines, flux tubes, and so on, domain walls, okay? In symmetry broken phases. There are global symmetry principles that describe these things. And then every time you have one of these objects, you should apply these global symmetry principles to make sure you're describing it in the correct way. And this is very nice because, first of all, there's many concrete things you can do with them, and I talked about a few of them. But I think more philosophically, you can ask the following question. You know, I started the thing by saying, what is a gauge theory? Okay, and more generally, what is the point of gauge theory? I think one thing that you might imagine is that the point of gauge theory is to describe local dynamics, is to describe extended objects in a sort of local way, all right? So you have local objects like flux tubes, and you try to describe them with local fields like A, and the way you do that is by sort of sewing together A in different patches by gauge transformations, which basically are what you use to guarantee that your flux tubes can't end. Now this is fine, but you might wonder, you know, the framework that we've developed here sort of gives you a way to organize your dynamics not around those gauge fields, but rather around the sort of integrity of the extended objects themselves. And so this is, I think, a very fruitful line of study. There have been many developments over the last few years, but I really think we're really only at the beginning of seeing what sorts of things we can do with this. Anytime you have an extended object, you should really revisit this formalism and see if it's helpful. And my final exercise to you is that I don't really know where this is all going to lead, but it's for all of you now to take this formalism and use it to derive all kinds of new things. Okay, thank you. That's the end of my lectures.